In this problem, we have a pulley system, and on this end of the pulley, we have an oscillator. So it's putting some oscillation frequency into the string, right? And it's doing that at 60 hertz. The length of the string in total is 1.5 meters. That's going to stay constant. And the linear mass density is 3.6 times 10 to the negative 4 kilograms per meter. Okay. We are asked for the first, second, and third harmonic, what mass do we need to achieve this? Now there's a couple of important formulas here that we need. Is that the speed of a wave on a string is equal to the square root of tension over the square root of the linear mass density. Another important formula that we're going to need to make a substitution with is this one here, that frequency equals the node that we're on times the speed of the wave over 2L. I did a little rearrangement here to find that the speed of the wave is equal to 2FL over N. Okay? Let's just kind of work through this problem here. So we don't know what tension is. That's the only thing that I see between these two. And let me actually set up the problem first. That would be kind of helpful, wouldn't it? So let's say that the speed of a wave on a string is equal to the force of tension with the square root of that over the square root of the linear mass density. Okay? We also say that the speed of a string wave, or any wave really, is equal to 2FL over N. Now that we have a V as a common term, right, we can set them equal to each other. So let's go ahead and do that. 2FL over N is equal to square root of T over square root of mu. Okay? So now that we have that, we can simply solve for what we're looking for. And in this case, it's going to be mass. But you don't see a mass term in there, but there is a term we can expand to get the mass, right? And it's one that we don't know, and that's tension. We're not at all given tension in the problem. If you look all over the board here or on wherever you see this problem, they do not give you a mass. You need to get that from the force of tension. So we now have to go back to what we learned very early on in the year. So mass M, I'm just bringing this down. What are the forces acting on this block? Well, we know going down is always going to be mass times gravity. And going upwards, keeping it at rest, is force of tension. Notice how I said it's at rest, right? If the only forces acting on these are these two, and they're opposite in direction, but equal in magnitude, and if it equals 0, then of course they need to cancel each other out, right? Because the body's not moving. It's not moving up or down, right? It's a pulley at rest. Okay, so we could say that the force of tension minus mass times gravity is equal to 0, right? All we have to do is bring over one of the terms, right? And we see that the force of tension is equal to mass times gravity. Okay, so let's do another simplification here. The force of tension we're actually going to say is actually the square root of mass times gravity, right? So we'll substitute in here mg. Now it should seem a little bit more solvable. You're looking at it, you're like, oh shit, that algebra looks hard and annoying. And it kind of is. But we're going to have to go through it here. So we're going to bring up our linear mass density, and we're going to divide by the square root of gravity. Okay? Or actually, there's a mistake that you can make that I do want to cover. So 2FL over N, and then this is multiplied up times the square root of the linear mass density is equal, over N is equal to the square root of mass times gravity. Now I'm going to keep it as this because we can't split the radical up here, right? You multiply terms together. You can't really do that. So what we're going to do to keep things simple is I'm going to work through using this formula that we derived. I need a calculator quick. We're going to just do a simple plug and chug for this side because we have every term that we need. It's going to be 2 times the frequency, 60 hertz, times the length of the string, 1.5 meters, times the square root of our linear mass density, 3.6 times 10 to the negative 4th. Okay, so let me plug that in quick. Okie dokie. And then we're going to divide that by which node we're on. So for the first node, we'll say that we are this whole section on the first node. And I'm going to write these values for this over here. So 3.42. So instead of that, now it's divided by 2. That's going to be 1.71, okay? Now let's divide it by 3. 0.5, and we'll round that to 7. Okay, so these are what this is equal to. There's no inherent meaning to them, it's just relative values that we're going to be using, okay? So now that we have those values, we can just simply solve for mass times gravity. Let's solve for the first harmonic here. So for the first harmonic, I'm going to say that the 3.42 is equal to the square root of mass times gravity. We're going to take the square of both sides, and we know that squaring a square root will just get rid of it. But 3.42 squared is 11.7, and then we're left with mass gravity. We divide the 11.7 by gravity, 9.81 meters a second. We're going to get that the mass that we need is 1.19 kilograms. Okay? And I'm sure the units would work out, but you'll just have to believe me on this one, because I don't really want to waste your time and go through all the unit canceling, because for simple problems it's okay, but for these complex ones it gets a little fuzzy. So for the mass one, we're going to need a mass of 1.19 kgs. Okay? Let's now do the same set of steps, but for the second harmonic. So the second harmonic, we got this whole value here to be 1.71. Okay, we're going to equal that to the square root of mass times gravity. All right, same process. We are going to take the square of both sides, divide by gravity. We're going to see that mass here is equal to 0.2, or we'll round it to 0.30 kgs. So the mass you need for the second harmonic is kind of a lot lighter, 0.30 kgs. Notice it's not like a 1-to-1. It's like, let's see if I can find a relationship here actually. Divided by 0.3. About 4 times, so it's a square difference. I'm sure that you could work that out using this idea here. But now let's move on. Okay, so for the third harmonic, our value for this piece here was 0.57. We're going to equal that to the square root of mass times gravity. I'm sure you already beat me to it while I was yapping, but we're going to square that value divided by 9.81. The mass of this is going to be even less, 0.331 kgs. All right, so for our final answer here, fully spelled out, given that the oscillator has a frequency of 60 hertz, linear mass density of 3.6 times 10 to the negative 4 kgs per meter, and a string length of 1.5. Given that it's a pulley system, we know that for the first harmonic, that mass needs to be 1.19 kilograms. For the second harmonic, to be shown on that oscillator, we need it to be 0.3 kilograms, and for the third harmonic, we need to bring that down to 0.0331 kilograms. Hope you enjoyed this episode. If you did, please drop a like, subscribe, and comment if you have any questions. I would love to answer them. Have a wonderful day.